Honors Chemistry. This is Lesson 10 on balancing equations. Antoine Lavoisier is known as the father of chemistry. Lavoisier was a wealthy government official who was able to afford the best measurement equipment available in the late 1700s. Lavoisier was able to break water, H2O, into H2, hydrogen molecules, and O2, oxygen molecules, then recombine these into exactly the same mass of water that he began with. Lavoisier's conservation of mass principle meant that the mass of the elements used in a chemical reaction remained the same after the reaction was completed. So no mass is either gained or lost in a chemical reaction. So this is a chemical reaction of methane gas, CH4, with oxygen. It has a name that we'll get into later in this unit called a combustion reaction. It's basically the gas that comes out of the outlets in the classroom, in a chemistry classroom, and you light a match to it and it produces carbon dioxide and water. So this is called a particulate diagram. It's meant to give you a visual image of how it could be more than one, but how a single molecule or atom of compounds will break apart and then recombine. So particulate diagrams provide a simple picture of the motion of atoms in a chemical reaction. The way that chemical compounds break apart and recombine requires advanced study of chemistry. Basically what it comes down to is they smash into each other and they break apart. And we'll study that in a subject called kinetics. Particulate diagrams show a beginning and final diagram of a reaction. It might also show an intermediate state of the reactants. I like to draw them like this, where you have the beginning reactants over on the left. You see how they break apart, and then we're going to see how they combine here, like this. So we can think of Lavoisier's conservation of mass principle as meaning that the number of atoms before and after a chemical reaction stay the same. So the mass stays the same, but we tend to think of it that the number of atoms stays the same. Before the reaction you had one carbon atom. After the reaction's over you still have one carbon atom. Before the reaction over on the left you had 4 oxygen. Over on the right you have 4 oxygen. Same with hydrogen. You started with 4 hydrogen atoms, you end with 4 hydrogen atoms. So you can't, this was one of Dalton's atomic principles of his atomic theory, is that you're not going to create or destroy any atoms in the process. They're simply rearranged. Chemical reactions are the centerpiece of the study of chemistry. Chemical equations are a recipe that shows how reactants combine into new substances called products. So here's that same chemical reaction. It's methane, CH4 plus oxygen gas produces CO2 and water. Of course, as you know, when you want to burn something, you have to light a match to it. That's called activation energy. We'll talk more about that also when we get to the subject of kinetics. But that's simply the chemical reaction. So we have symbolism. We use the chemical symbols that the periodic table has. Remember, those symbols are international. So no matter what language someone speaks, this will be the formula for the combustion of methane. So on the left, they're called the reactants. And on the right they're called the products. That's what's produced. Now we'll get into chemical reactions later that can actually move backwards. They can move from products to reactants. But the natural way for this reaction to happen is to go from the left reactants to the right products, just like you read a sentence from left to right. The one-way arrow indicates that the reaction moves from left to right. It really indicates it moves from left to right only. It can't go backwards. This particular reaction cannot go backwards from products to reactants. So there's 2 ways to balance an equation. The first way is kind of the simplest way, but it takes a lot of space, and you want to eventually move past this. And we call this the box method. So an equation must be balanced before it can be used in chemistry. If the equation's not balanced, it's of no use to you in doing any kind of chemical analysis. The first method is called the box method. This is a good method for beginners. So what you do is you take this compound, this chemical reaction up above, and you break each of the atoms into separate letters. So the first compound there is V2O5, so you create 2 V's and 5 O's. HCl, hydrochloric acid, you create an H and a Cl. VOCl3, you have a V, an O, and 3 Cl's. And for water, H2O, you have 2 hydrogen, 2 H's, and an oxygen. Now what you do in this method is you just pick an element that you want to balance first. One thing you should avoid is any element that appears more than once on the same side of the arrow. So if you look at oxygen, it appears in 2 different compounds over on the right side. It appears in VOCl3 and in H2O. By appear more than once, I don't mean has more than one atom. That's okay, but you only want to see it in one location there. So you want to stay away from oxygen. It often appears in multiple locations in chemical reactions. So you want to pick something else. All right, hydrogen would be fine, vanadium would be fine, the V or the chlorine would be fine. So we're going to go ahead and we're going to start with the V. And so what you do is you notice that you have 2 V's on the left and 1 on the right. So you draw a box underneath the one that has the least of those numbers. So you have 1 V on the right, 2 on the left. So you want to draw a box underneath the V that's on the right so that you create a second V. Now you'll notice you have 2 V's over on the right side. You can't just draw the V, however, write the V. You have to do everything that's in that compound. So you have to include another O and 3 more Cl's. So now we have vanadium in balance. We have 2 on the right and 2 on the left. Now we're going to go ahead and we're going to balance the chlorines. So you look over on the right side. After you added that second box to VOCl3, you now have 6 chlorines. That means we need to go over to the left and create 6 chlorines. So we're going to write HCl 6 times. There it is. So, and we didn't change the balance of the V's. So you still have 2 V's on the left, 2 V's on the right. You now have 6 Cl's on the left and 6 Cl's on the right. So V and Cl are in balance. Remember, we're going to save O until the very end. So the only thing we have left then other than that is hydrogen. So look how many hydrogen you have on the left. You have 1, 2, 3, 4, 5, 6. How many do you have on the right side of the arrow? You have 2. So you're going to have to add 2 more boxes for water, so you have a total of 3. So there's another H2O, there's another H2O. So now V, H, and Cl are all in balance. Just look at it for a second, convince yourself that that's true. So now let's see what we have for O. Well, look what happened. Magically, the O balanced at the end. That doesn't always happen, but many times it does. So you have 5 oxygens on the left. You always had that. You had the O5 there from the very beginning of the problem. But now you have 5 oxygen O on the right. So everything is in balance. You have 2V on both sides. You have 5O on both sides. You have 6H on both sides. And you have 6Cl on both sides. So then you write coefficients. When you balance an equation, you cannot change the subscripts. That V2 stays a V2. That O5 stays an O5. You can't change those little numbers. All you can do is put coefficients in front of each of the compounds. And you simply do that based on how many boxes of each compound you have. Okay, so now what we simply do is you go ahead and write coefficients in front of the each of the compounds, based on how many boxes you have. So you have 1 V2O5, you have 6 HCl, you have 2 VOCl3, and you have 3 H2O. So those are the coefficients. Again, you cannot change the subscripts. That V2O5 cannot change. What you can change are the coefficients in front. So what they mean is the following. It means you have 1 molecule of V2O5 plus 6 molecules of HCl will produce 2 molecules of VOCl3 plus 3 molecules of H2O. So if you count, you'll see, as we just did, that you have the same number of atoms of each type on the left side as you have on the right side. Yeah, again, you have to do that before you can use this chemical equation in any kind of analysis. Let's move on and see a different method, really a little bit more sophisticated method that you eventually want to do, because as you can see, the box method can take up a lot of space on your page. You don't always have a lot of space to work with. So here's the same equation, and the second method is the standard way to balance a chemical equation. So the first thing you do very simply is you take each of the elements and you write them in a column right below the arrow. You'll see some books that put them over to the left side or something. I like to write them in the middle so we can see that they're balanced on both sides. So let's just count how many atoms we have of each element. So for V, we have 2 on the left and we have 1 on the right. So just confirm that you understand why that is. Again, the subscripts are how many atoms of each element. The coefficients tell you how many molecules you have of a particular compound. Okay, the O, how many O's on the left? See if you can do these on your own. 5, how many do you have on the right? Okay, remember you have O's in 2 different locations, in the VOCl3 and in the H2O, so you have 2 over on the right. H's, 1 on the left, 2 on the right. And chlorine, Cl, 1 on the left, 3 on the right. So what you got to do is get those numbers to where they're all equal so that everything is balanced. Okay, so what are we going to start with? Well, we'll go ahead and we'll put a 2 in front of VOCl3. What that means is we now have 2 V's on the right, and we already had 2 V's on the left. So the V's are now in balance. But what we also changed when we put that 2 out in the coefficient, it distributes just like in math, just like you do a distribution through. You also now have 2 O's on the VOCl3, and you now have 6 chlorines. You have 2 times Cl3, which is 6 chlorine atoms. So you have to be sure you change all of those. So what we're going to do is just put lines through it. So for the V, we put a line through the 1 and we turn it into a 2. So now the V's are in balance. Okay, now we're not ready to deal with O yet. Remember, you stay away from that because it appears in more than one place on the right side of the equation. So stay away. You do have to change it, but we don't want to try to balance it next. But we're going to go ahead and change it. So now how many oxygens do we have? Now be careful. You now have 2 oxygens in the VOCl3, but you still have that 1 over there in the water molecule. So that's a total of 3 oxygens on the right side. Finally, the Cl3, that went from being 3 to being 6. You doubled that. That 2 applies to the Cl3 as well, so you now have 6 chlorine atoms. Okay, now we're going to do what we did in the last method. We're going to go ahead and balance the chlorines. So we put a 6 up there above HCl to balance the chlorines. Again, what you do is you just kind of go back and forth. You pick one element at a time to balance. So we now have 6 chlorines. And we also have 6 hydrogens. So I went ahead and changed the hydrogen first. It doesn't matter. So I have 6H, and I changed that. And now we changed the chlorine, and we have 6Cl. So what's in balance so far? So far we have the V's in balance, and we have the Cl's in balance. Okay, we still have the O's and the H's to balance. Okay, again, we're going to stay away from oxygen, go to hydrogen. So what do we do to balance hydrogen? See if you can do this one on your own. You have 6 on the left and 2 on the right. So what are you going to do? You're going to do this. Put a 3 up there in front of the water molecule. By the way, the reason I'm writing them up above like this, that's the way I do this, is because that may not be the final coefficient. You may need to change those coefficients again. They may change again. So you don't want to put them right in front of the compounds, which is normally where they should be placed. So now we have 3 H2O, which means we have 3 H's. That's a total of 6 H's. 3 times 2 is 6 hydrogen atoms, and we have 6 on the left. So now we can balance the hydrogen. So now everything's in balance except oxygen. So let's see if it is. So on the right, we have 2 oxygen in the VOCl3, and we have 3 more in the H2O. That's a total of 5 oxygen. And over on the left, we see we have 5 oxygen. So actually the oxygen are in balance. Again, if you save those until the end, the ones that appear in more than one place, oftentimes you'll find they balance out by the end of the equation. By the time you're done, you didn't have to do any extra work. So that means we're going to balance the oxygen, make it 5 on the left. It's going to be 5 on the right to balance the 5 on the left. So if you look at the numbers I have there, everything is in balance. 2V, 2V, 5O, 5O, 6H, 6H, 6Cl, 6Cl. So everything's in balance, so you can go ahead and write the equation down at the bottom. Okay, so there you go. There's the final equation down at the bottom. Everything balances. 1V2O5 plus 6HCl produces 2VOCl3 plus 3H2O, the exact same equation balancing that we obtained in the previous using the box method on the previous slide. Okay, now we're going to have a quick lesson on atomic mass calculation. You remember the atomic mass on the periodic table is at the bottom of each element entry, and it tells you the average mass of all the isotopes of that particular element. And that's why it's a decimal number, because it's an average. So it comes out to be somewhere in between the whole numbers. So this is just a quick lesson on how do you do that calculation. So a weighted average computes the average using the percent or fraction of each value. So for example, find the weighted average of the following. So if we were just asked to find the average of 12 and 15 and 20, you'd add up 12 plus 15 plus 20 divided by 3. But here you have 5 12s, you have 3 15s, and you have 2 20s. Well, you could use that same method. You can add all the 12s together, all the 15s together, all the 20s together, and if you count, there's 10 values there, 10 different numbers. That would divide by 10, and what you would get is 14.5. So you can add all the numbers and divide by 10, the number of values, to get an answer of 14.5. In chemistry, though, that's not practical. You're dealing with numbers of atoms and molecules that are countless. I mean, it's just so big you can't possibly count them all. So we have to have another way to find average masses. So one way you can do it is by using fractions. So another way to approach the problem is to take the fraction of the total values of each value. So for example, find the weighted average of the following. So you know you have 12 values there. 10 values there. You have 10 values there, so 5 of the 10 are 12s. So the fraction of the total number of values that are 12 is 5 out of 10. So if you take 12 and multiply it by 5/10, you get 6. Now 15, there's 3 15s, so 3 out of 10 of the values are 15, so that's 3/10. If you take 15 and multiply it by 3/10, you get 4.5. Do the same for 20. 2 out of the 10 values are 20s. So 20 times 2/10 equals 4. If you then take those 3 numbers that you obtained, the 6.0, the 4.5, and the 4.0, you add those together, you get the weighted average of 14.5, the same number we got on the previous slide by simply counting them all, adding them all up, and dividing by 10. Okay, so this is more practical if you have a large number of numbers and you know the fraction. Typically, though, in chemistry, we don't know the fraction, we know the percent, which is kind of the same thing, but we know the percentage. So let's go look at an example of that. So more commonly in chemistry, isotopes are expressed as a percentage of all isotopes of that element. So first of all, let's remember how you work with a percentage. So you have to remember how to, if you're giving a percentage like 32%, so convert a percentage to decimal form. Percent means per 100. That's what the word percent means. So example, 32% equals 32 over 100. And if you do that on a calculator, 32 divided by 100, you get 0.32. So if you want to think of an easy way to remember it, you just take the decimal point in 32, which is behind the 2, and you slide it 2 places to the left, take away the percent sign, and you get 0.32. So you don't have to calculate it every time, okay? Just do that. Slide the decimal 2 places to the left. Okay, so let's take an example here of calculating the atomic mass. So a sample of the element huvarium contains the following isotopes. So huvarium 20 is 82%. Huvarium 21 is 16%, and Huvarium 22 is 2%. If you add those percents up, it comes out to be 100%. So that means you have all of the elements of Huvarium that exist. How do you know this, by the way? How do you know that 82% number, that 16 and that 2%, if you can't possibly count some massive number of Huvarium atoms? And the answer is a technique we studied earlier, which was mass spectrometry, where you run them through a magnetic field, you fire them off down a tube, you run them through a magnetic field. The heavier one curves the least, the slowest. The lighter one curves faster. Remember the motorcycle and the truck example? And you can tell by looking, go back and review the slide on mass spectrometry, but you can tell by looking at, you can see what percent. You may not know the exact number, that's too massive a number to count, but you can know what percent of the atoms were the heaviest, what percent were in the middle, that's the 21, and what percent were the, in the middle, and what percent were the lightest, that's the 20. Okay, 22 the heaviest, 20 being the lightest. So now what you do is you simply take the 20, that's the mass number of Huvarium 20, it's the total number of protons and neutrons added together, which each one has a mass of 1 atomic mass unit. So the overall atom, that overall isotope, has a mass of 20. You multiply it by the percent in decimal form, 0.82, and you get 16.40. I'm a little loose on the significant figures here. It probably shouldn't be that many. 21, same thing, 16%. So 21 times 0.16 is 3.36. And 22 times 2% is 22 times 0.02. Don't forget that 0 after the decimal point. It's not 0.2, it's 0.02. Okay, you multiply that, you get 0.44. Now you simply add those numbers together, and you get 20.20. So that would be the atomic mass of Huvarium, of all of the different isotopes averaged together. The atomic mass, that's what you would see on the periodic table. If there really was such an element as Huvarium, you would see the atomic mass as 20.20. Okay, so that's how you compute atomic mass. All right, that takes care of this lesson. So we covered balancing. You really do want to become proficient at that. And I'll give you an assignment with about 10 problems or so, and show you a couple little tricks and tips on it also. So I would watch the answers video when I do get that up. That's not up yet, and watch the answers video for that. Okay, so you have a good day, and we'll see you in class.